Hello Calc 3 and welcome back to another video. In this video we'll be covering section 14.5 on the directional derivative and gradients. So let's start off by recalling from the last section, section 14.4, that if we have a function in two variables, f of x, y, and that function is differentiable, then the rate at which f of x, y changes with respect to some parameter t along the curve given by x equals g of t and y equals h of t is given by this expression down here. And this expression was developed with the chain rule. So what we're saying here is that if I have a curve that's parametrized by x equals g of t and y equals h of t, then I can find the rate of change of my function f with respect to the parameter t, and to do so we use the chain rule. So keep that in mind as we go into the following discussion where we're going to develop the notion of a directional derivative. So let's say we have a function in two variables, f of x, y, and the domain of the function is the region that I have drawn in yellow here. So the domain is going to be all of the area enclosed by that yellow loop. And we can let P naught be some point inside of the domain of our function, and we can construct unit vectors that start at our point P naught that point in different directions. So I have one unit vector that's already drawn, but we could draw other unit vectors as well. I can draw a unit vector that goes up, I can draw a unit vector going to the left or in any kind of different direction as long as it starts at the point P naught. Then we can parameterize the line that goes through the point P naught that is parallel to whichever unit vector u we choose. And that parameterization is going to be given by x equals x naught plus s times u1, where u1 is the x component of our unit vector, and y equals y naught plus s times u2, where u2 is the y component of our unit vector. And notice that I've used the parameter s here because I'm specifically referring to the arc length parameter of the line. So recall from section 13.4 that the arc length parameter tells us how far along the line in a certain direction we have traveled. And in this case, the derivative of our function f with respect to s is going to give us the rate of change of f with respect to the distance traveled along whichever line we have parameterized. And as we change our unit vector u so that it points in different directions, we can calculate the derivative of f with respect to s to find the rate at which f changes as we pass through the point P naught in different directions. So remember from section 14.3, where we introduced the concept of the partial derivative, that the partial derivative with respect to x gave us the slope of the tangent line at a certain point as we approached purely in the x direction, and the partial derivative with respect to y gave us the slope of the tangent line at a given point as we approached purely in the y direction. With a directional derivative, this gives us the ability to approach the point in all kinds of different directions, along any different direction. And we're going to get unique slopes for the tangent lines as we approach from different directions. So slopes that are different than even just the partial derivative with respect to x or y. So this leads us into our first definition. The derivative of a function f at the point P naught in the direction of the unit vector u, which is equal to u1i plus u2j, is going to be the number, and this is given by, so on the left side of the equation here, we have the derivative of f with respect to s along the vector u at the point P naught, or in the direction of the vector u at the point P naught, is equal to the limit as s goes to 0 of this difference quotient that I have drawn over here. So we have f of x naught plus su1, y naught plus su2, minus f of x naught y naught all divided by s. And as long as this limit exists, this is going to be the direction or the derivative of the function f in the direction of the vector u at the point p naught. And we denote this directional derivative by this expression that I have down here. So we have a capital D sub u of f and then sub p naught to show that we're evaluating at the point p naught. So here's my first remark. Note that the partial derivative of f with respect to x and the partial derivative of f with respect to y are the directional derivatives of our function f at the point p naught in the I and j directions respectively. So as I already said, the partial derivative with respect to x is the directional derivative where we are approaching the point in purely the x direction. The partial derivative with respect to y is the directional derivative where we approach the point in purely the y direction. So let's move on to our first example where we are calculating a directional derivative. So we want to find the derivative of the function f of xy is equal to x squared plus xy at the point p naught, which is just 1, 2, in the direction of the unit vector, which is 1 divided by the square root of 2i plus 1 over the square root of 2j. And we're going to use the definition of the directional derivative to calculate here because it's the only information that we've developed so far. So by definition, the derivative of f in the direction of u at the point p naught is equal to this expression up here in the box. So we have the limit as s goes to 0 of f of 1 plus s times 1 over the square root of 2, 2 plus s times 1 over the square root of 2, minus the function evaluated at 1, 2, all divided by s. And from here it really just becomes a problem of plugging these expressions back into the function and then doing some algebra. So notice that this 1 plus s times 1 over the square root of 2 is squared because it is our x that we're plugging into the function f of xy. Then we also have plus xy if we're looking at the function up here. So we have 1 plus s times 1 over the square root of 2 multiplied by 2 plus s times 1 over the square root of 2, where this is x and this is y. And then of course we can just plug the point 1, 2 back into the function and get 1 squared plus 1 times 2. We can do a little bit of algebra here and expand, and we end up with a bunch of different constants that cancel. So we have a 1 here that's going to cancel with this minus 1. We have a 2 that's going to cancel with this minus 2. And then if we combine the like terms that are left, we end up with the limit as s goes to 0 of 5 times s over the square root of 2. So you can see those terms coming from here, plus s squared, where we have this 1/2 s squared plus 1/2 s squared that are being combined. And we can remove an s from each of the summons in the numerator here, and we end up with the limit as s goes to 0 of 5 divided by the square root of 2 plus s. And at this point we can plug in 0 for s, and we get that the limit is ultimately equal to 5 divided by the square root of 2. So what this tells us is that the rate of change of our function f at the point 1, 2 in the direction of u is equal to 5 over the square root of 2. So that'll be the directional derivative. Okay, so here I want to go back to the interpretation of the directional derivative. So why do we calculate the directional derivative? What is its purpose? Well, imagine that we have a function in two variables, so f of x, y, and it's going to describe the altitude of a mountainous region throughout some plot of land. So you can think of the plot of land as the plane, and each of the different locations on the plot of land corresponds to some ordered pair. And the function f of xy is going to give you the elevation of the land at whatever point you're on. So you enter the coordinates of the land, and f is going to return the height of the land at that point. So you can think that when f is really big, maybe you have a mountain. When f is really small, maybe you have a valley around that area. Now imagine yourself standing on the side of some mountain in the region. Then the directional derivative is going to correspond to how steep the climb would be if you were to walk in any direction from your spot. So I have somewhat of a pitiful drawing here to describe what I'm talking about. I have a mountain in green, that's the best I could do, and then you are just a point standing on the side of the mountain, and you can see that if you were to walk up the mountain, and f would be getting higher and higher as you go up the mountain, the directional derivative is going to be positive because the slope of the mountain in the direction you're traveling is up. Whereas if you walk back down the mountain, then f is going to be getting smaller and smaller as you travel. So the slope is going to be negative. And if you walk along the side of the mountain, so you never go up the mountain, you never go down the mountain, then the directional derivative is just going to be 0 because f isn't going to be changing at all. Your elevation is staying the same even though you're walking. So hopefully this is a helpful depiction of what the directional derivative means and why we would calculate it. So now that you hopefully have a pretty good understanding of what the directional derivative is, why we would care about it, let's try and find a better method to calculate the directional derivative, because all we have up until this point is the definition, and I don't think most people want to be calculating the limits of difference quotients all day. So let's find a different way to calculate the directional derivative, and we're going to develop it here. So let f of xy be differentiable, and consider the line that's parameterized by x equals x naught plus s times u1, and y equals y naught plus s times u2. So these are just the parameterizations we had at the beginning of the video. And we also have some point p naught, and s is the arc length parameter, and then we have our unit vector u given by u1i plus u2j. Okay. So by the chain rule from section 14.4, we know that the derivative of f with respect to s in the direction of the vector u at the point p naught is given by the partial derivative of f with respect to x at the point p naught times the derivative of x with respect to s, so that's this product here, plus the partial derivative of f with respect to y at p naught times the derivative of y with respect to s. So again, this is just an application of the chain rule for a function of two variables from section 14.4. Now notice that the derivative of x with respect to s is just going to be u1, since x is equal to x naught plus s times u1. And likewise, the derivative of y with respect to s is just going to be equal to u2. So we can substitute both of those expressions in for dx ds and dy ds respectively. And now this gives us that the derivative of f with respect to s in the direction of u at the point p naught is equal to partial f with respect to x at p naught times u1 plus partial f with respect to y at p naught times u2. And this starts to look like a dot product. So we can split these two products here up into the dot product of two vectors. And in the first vector, we have partial f with respect to x at p naught, partial f with respect to y at p naught, and then we have the dot product with the vector u1, u2. So this here is just our unit vector u, and this other vector is something we haven't defined yet, but we're just about to, because it shows up in this equation here. So here's our definition. The gradient vector of f of xy at a point p naught is the vector, and you can call this the gradient of f. You could also call it del f, because this symbol here is del, and it's going to equal the vector where in the x component we have the partial derivative of f with respect to x, and in the y component we have the partial derivative of f with respect to y. And we obtain the gradient vector at different points by evaluating the partial derivatives of f at the point p naught. So if we want specifically the gradient vector at a point p naught, then we're going to plug the point p naught into the partial derivative of f with respect to x, and then the partial derivative of f with respect to y, and the resulting vector will be the gradient at that point. And now, here's the big theorem. This is why this is helpful in calculating the directional derivative. So if f of xy is differentiable in a region containing the point p naught, then the derivative of f with respect to s, or just the directional derivative, in the direction of the vector u at the point p naught is equal to the gradient vector evaluated at the point p naught dot product with our unit vector u. And this is actually just a consequence of what we developed right here. So we showed up above that the directional derivative is equal to this gradient vector dot product with our unit vector u, and down here in the theorem we're just making that explicit. So this should give us another way to calculate the directional derivative that is certainly simpler than the limit definition that we've had up until this point. So let's do an example here. We want to find the derivative of the function f of xy is equal to x times e to the y plus cosine xy at the point 2, 0 in the direction of v is equal to 3i minus 4j. So notice right off the bat that v, as it's given to us, is not a unit vector. So we're going to have to find the unit vector in the same direction as v, and then apply the theorem from above to calculate the directional derivative. So I'm actually going to do that first. So if you look down here, we have that u, our unit vector in the direction of v, is going to be equal to v divided by the magnitude of v, which is equal to 3i minus 4j over 5, since the magnitude of v is equal to 5. Or we can just write it in this form here. The I component is 3/5 and the j component is minus 4/5. And now let's go back up top to work on the gradient vector. So for the gradient vector, we're going to need the partial derivative with respect to x and the partial derivative with respect to y. So we start off with the partial derivative with respect to x, and we get e to the y minus y times sine of xy, and then the partial derivative of f with respect to y is equal to x times e to the y minus x times sine of xy. And to find the gradient vector specifically at the point 2, 0, we're going to evaluate both of these partial derivatives at the point 2, 0. So for the partial derivative with respect to x, we plug in 2 for x, we plug in 0 for y, and we end up getting 1 as the value. For the partial derivative with respect to y, again we plug in 2 for x, and we plug in 0 for y, and we end up getting 2 as the value. So now the gradient vector at the point 2, 0 is going to be equal to the vector with 1 as the I component and 2 as the j component. And finally, by the theorem above, the directional derivative in the direction of u at the point 2, 0 is going to be equal to the gradient vector at the point 2, 0 dot product with our unit vector u. So we have the vector 1, 2 dot product with the vector 3/5 minus 4/5, and then just computing that dot product, we end up with the value -1. So this tells us that the change in our function f with respect to the arc length parameter s along the line in the direction of this vector here at the point 2, 0 is equal to -1. Okay, so let's develop some properties of this directional derivative. And we're going to start out by, again, recognizing that the directional derivative is given as the dot product of two vectors. So it's the dot product of the gradient vector and the vector u that gives us the direction of our derivative. But by definition, that dot product will equal the magnitude of the gradient vector multiplied by the magnitude of u times cosine of the angle between them. But u is just a unit vector, so its magnitude is going to be equal to 1, which means that ultimately the directional derivative is equal to the gradient of f, or I should say the magnitude of the gradient of f, multiplied by cosine theta, where theta is the angle between u and the gradient of f. And once we understand the directional derivative in this way, we can immediately get some properties about the directional derivative. So the first property is that our function f is going to increase most rapidly when theta is equal to 0 and u is in the direction of the gradient of f. So why is this the case? It's because if we look up at this expression, which I've just underlined in purple, the function is going to increase most rapidly, or the directional derivative is going to be biggest. Both of those phrases are synonymous. When we maximize this expression. And that expression is maximized when cosine of theta is equal to 1. And for cosine of theta to be equal to 1, we need theta to equal 0. So in other words, f is going to increase most rapidly in the direction of the gradient vector at any point in the domain of f. Likewise, our second property here, f is going to decrease most rapidly in the opposite direction of the gradient of f, or in the direction of minus the gradient of f. And let's see if we can figure out why this is. Again, look up at the expression that I have underlined in purple. To find where f decreases most rapidly, we want to minimize this expression. And that expression will be minimal when cosine of theta is equal to minus 1. And for cosine of theta to equal minus 1, we need theta to equal 180 degrees, or pi. And for that reason, this gives us that f is going to decrease most rapidly when we're going in the opposite direction of the gradient vector, because we want the angle between the gradient vector and our unit vector giving us the direction to be pi. And thirdly, any direction u that is orthogonal to the gradient vector is a direction of 0 change, since cosine of theta is going to be equal to cosine of pi over 2, which is just equal to 0. So remember that u being orthogonal to the gradient vector f means that the angle between them is going to be pi over 2, or 90 degrees. And when that happens, the directional derivative, which is now given by this expression underlined in purple, is going to be 0. Because cosine of theta is going to be equal to 0. So these are the three properties that we can get just from looking at the directional derivative in that way. So let's move on to an example where we're going to apply these different properties. So we want to find the directions in which the function f of xy is equal to x squared over 2 plus y squared over 2 does the following things. We want to find the direction in which it increases most rapidly at the point 1, 1, decreases most rapidly at the point 1, 1, and has 0 change at the point 1, 1. So we're just going to use the properties that we have right here to find all of this different information. So first we need an expression for the gradient vector. So the gradient of f is going to be equal to the vector where the I component is the partial derivative with respect to x, and the j component is the partial derivative with respect to y. If we take both of the partial derivatives, we find that the gradient is equal to the vector xy. And now we want the gradient vector specifically evaluated at the point 1, 1. And so we plug in 1 for x and 1 for y, and we get that it's just the vector 1, 1. And the direction of 1, 1 is going to be given by the vector 1 over the square root of 2, 1 over the square root of 2. Where here we've just taken 1, 1 and we've divided by the magnitude to make sure that it is a unit vector in the same direction. So this is going to be the direction in which f increases most rapidly at 1, 1, because we know that f increases most rapidly in the direction of the gradient vector at 1, 1. Now let's move on to part B, the direction in which f decreases most rapidly. Well, we know that's going to be minus the gradient vector of f evaluated at 1, 1, which is equal to minus 1, minus 1. And then to just make sure that it has a magnitude of 1, so that it's a unit vector, we again divide by the magnitude of the vector minus 1 to get the unit vector minus 1 over the square root of 2 minus 1 over the square root of 2. So this will be the direction in which f decreases most rapidly at the point 1, 1. And now the third part of this question, part C, is going to be the most difficult of the three. So we want to find the directions where our function has zero change at the point 1, 1. So we know that this is going to happen along paths that are orthogonal to our gradient vector at 1, 1. So again, our gradient vector at 1, 1 is equal to the vector 1, 1. And we want to find vectors that are orthogonal to 1, 1. So we're going to let our vector, or we're going to let AB be some vector. And we're going to take the dot product of AB with 1, 1 and set it equal to 0. And we want to use this to solve for A and B. So we can hopefully find vectors that are orthogonal with 1, 1. So if this dot product is equal to 0, it means that A plus B has to be equal to 0, which just implies that A is equal to minus B. But we also want the vector giving the direction to be a unit vector. So we're going to also require that the square root of a squared plus b squared is equal to 1, which of course just implies that a squared plus b squared is equal to 1. And ultimately, this gives us that b is going to be equal to plus or minus 1 over the square root of 2. And we already have the fact that a is equal to minus b. And these two pieces of information now give us two orthogonal unit vectors. So vectors that are orthogonal specifically to the gradient vector at 1, 1. And these two orthogonal unit vectors will be 1 over the square root of 2 minus 1 over the square root of 2, and then we reverse the sign. So on the other one we have minus 1 over the square root of 2, 1 over the square root of 2. So these will be the two directions in which the function has zero change. All right, now I want to move on to a little bit of a different subject here. So ultimately, we're going to use the idea of a gradient vector from the previous section to develop a method by which we can find lines tangent to level curves for particular functions f of xy. So let f of xy be some differentiable function and assume that f of g of t h of t is equal to c for some constant c. And in particular, this g of t, h of t are the components of a curve, which is given by r here, in the domain of f of xy. So in other words, we have this curve r, which is given by g of t I plus h of t j, and that curve is going to be part of a level curve of f of xy, because if I take any point on my curve and I plug it into my function, the function is going to give out the same constant c. So r of t is going to be part of the level curve of the constant c, or corresponding to the constant c. So if this is the case, then I know that the derivative of f of g of t h of t with respect to t will equal the derivative of c with respect to t. So we're just taking the derivative of both sides of this equation up here. Well, the derivative of c is going to be 0, it's just a constant. And we have an expression for the derivative of f of g of t h of t, which is given by the chain rule from section 14.4. So that's what's happening on the left-hand side of the equation here. But now we can represent the left-hand side of the equation as the dot product of two vectors. Ultimately, it's the dot product of the gradient vector of f and the derivative of our curve r with respect to t. Because remember that if r of t is given by g of t I plus h of t j, then the derivative of r with respect to t is going to give us the vector where we take the derivative of each component of r, which gives us this vector dg dt dh dt. So ultimately, this allows us to say that the gradient of f at some point, dot product with the derivative of r with respect to t, is going to equal 0, and that's true for all points. So at every point x0, y0 in the domain of f of xy, the gradient of f is going to be orthogonal to the level curve that passes through the point x0, y0. And we can use this observation to find an equation for a line that's tangent to the level curve through some point. So first off, just a general note. The line that passes through a point P0 orthogonal to some vector n, given here as ai plus bj, is given by the equation a times x minus x0 plus b times y minus y0 is equal to 0. So this is similar to the way that we developed the equation for the plane. We had some normal vector and we had a point on the plane, and we used those two pieces of information to give us an equation for the plane. Here we're doing a similar thing, but we're getting an equation for a line, where that line passes through the point P0 and is orthogonal to the vector n. So we just discussed above that the tangent line to a level curve at a point P0 is going to be orthogonal to the gradient of f, because the slope of the tangent line, or I should say a vector that is parallel with the tangent line at that level curve, is going to be given by dr dt. So we know that that's going to be orthogonal to the gradient vector of f. Hence, if we have some point P0, then the line that's tangent to the level curve containing the point P0 is given by the partial derivative of f at x0, y0 times x minus x0 plus the partial derivative of f with respect to y at x0, y0 times y minus y0 is equal to 0. So again, this equation might look foreign right off the bat, but what we're really doing is taking the expression here that gives us the equation of a line through some point orthogonal to a vector, and we're just noticing the fact that the gradient vector is such an orthogonal vector. So here, this would correspond with A in the equation above, and this would correspond with B in the equation above. And then in this little box down here, I just explicitly write this out. So an equation for the tangent line to some level curve is given by f sub x at x0, y0 times x minus x0 plus f sub y at x0, y0 times y minus y0 is equal to 0. So this is an equation that you're going to want to keep in mind. So now I want to talk about some algebraic rules for gradients. You'll notice that all 5 of the rules that I have given in the box here will very closely mimic the rules for differentiation, so they should be pretty easy to memorize. So the first rule is the sum rule, which says that the gradient of f plus g, where f and g are both just some functions, we're adding them together. The gradient of f plus g is equal to the gradient of f plus the gradient of g. We then have the difference rule, which says that the gradient of f minus g is equal to the gradient of f minus the gradient of g. We also have the constant multiple rule, which says that we can take constants and we can just pull them out of the gradient when we're finding the gradient of some function c times f. And then fourthly, we have the product rule. So the gradient of f times g is equal to f times the gradient of g plus g times the gradient of f. And then finally, we have a quotient rule. So the gradient of f divided by g is equal to g times the gradient of f minus f times the gradient of g, all divided by g squared. So again, all of these rules should look very familiar because they just mimic the differentiation rules, and so you should be able to remember them pretty easily. And proving all of these different rules would be way too lengthy, but I will give a proof of just the fourth rule. I think the book offers a proof of rule 1 and 2 if you're interested. So let's let f of xy and g of xy be general differentiable functions in two variables. Then the gradient of f times g is defined to be the vector where the I component is the partial derivative with respect to x of f times g, and the j component is the partial derivative with respect to y of f times g. So this is the definition of the gradient. And now we can use the product rule that we have for partial derivatives to expand each of these components here. So the partial derivative with respect to x of f times g is equal to the partial derivative with respect to x of f times g plus f times the partial derivative with respect to x of g. So again, this is just using the product rule that we already have for partial derivatives. And for the j component, we expand in the same way. So we get the partial derivative with respect to y of f times g plus f times the partial derivative with respect to y of g. And now we can notice that this vector can be written as the sum of two different vectors. So in the first vector, we're going to have the partial derivative with respect to x of f times g, and the j component of that first vector is going to be the partial derivative with respect to y of f times g. And then in our second vector, we have as the I component f times the partial derivative with respect to x of g, and then in the j component, we have f times the partial derivative of y with respect to g. So again, the key here is just realizing that we can take this vector up here and write it as the sum of two different vectors. And now in this first vector, we can pull out g, since g is just a scalar function. And we end up with the vector given by the partial derivative with respect to x of f and the partial derivative with respect to y of f here, times the function g plus the function f. Again, this is a scalar function, so we can pull it out, times the vector which is given by the partial derivative with respect to x of g in the I component and the partial derivative with respect to y of g in the j component. And both of these vectors that are written here are just gradients of f and g respectively. So we end up with the gradient of f times g plus f times the gradient of g. And then to make it look like what we want it to look like, so we want it to look like f times the gradient of g plus g times the gradient of f, we just reverse the order of the sum here. And that should be the proof for the fourth property there. So at this point, we are almost done with the video. There are just a few loose ends that we should probably tie up. The first is to generalize the notions that we've developed to functions of three variables. So all of the notions that we have developed will generalize as naturally as possible. For example, for functions of three variables, f of x, y, z, we can extend the definition of the gradient by letting the gradient of f be equal to the vector where the I component is the partial derivative with respect to x, the j component is the partial derivative with respect to y, and then of course we have a k component now, which will be the partial derivative of f with respect to z. And the directional derivative is still going to be basically identical, so it'll still be defined as the gradient of f dot product with the unit vector giving us the direction of our derivative, and this will still equal the magnitude of the gradient times cosine of theta, where theta is the angle between u and the gradient. And for this reason, the directional derivative is still going to be greatest in the direction of our gradient, and least in the direction of minus the gradient, or in the opposite direction of the gradient. And in any direction orthogonal to the gradient, we still have that the directional derivative will be equal to 0. So let's do an example with a function in three variables just to solidify some of these ideas. So part A of our example is to find the derivative of f of x, y, z is equal to x cubed minus xy squared minus z at the point 1, 1, 0 in the direction of the vector 2i minus 3j plus 6k. So let's worry about A first and then come back to B. So again, notice that v, as it's given to us, this direction vector is not a unit vector, so we want to find a unit vector in the same direction as v. And to do so, we take v and divide it by the magnitude of v. The magnitude of v ends up being 7, so our unit vector in the direction of v will be 2/7 minus 3/7, 6/7. And now we want to find the gradient of f, which again is the partial derivative with respect to x, and the I component, the partial derivative with respect to y, and the j component, and the partial derivative with respect to z and the k component. And the partial derivative with respect to x will be equal to 3x squared minus y squared. You can check that out. If you want to, you can pause the video and just verify each of these partial derivatives. In the j component, we have minus 2xy, as that's the partial derivative with respect to y. And the partial derivative with respect to z is going to be equal to minus 1. So that'll be the k component of our gradient. Now we can find the gradient vector at the point 1, 1, 0 by plugging in 1 for x, 1 for y, and 0 for z. And we end up with the vector 2, -2, -1. And now to find the directional derivative, or the derivative in the direction of u at the point 1, 1, 0, we take the dot product of our gradient vector at 1, 1, 0 with our vector u, which is the unit vector in the direction of v. And this is, of course, 2, -2, -1, dot product with 2/7, -3/7, 6/7. And ultimately, that will give us an answer of 4/7. So the derivative of our function f at the point 1, 1, 0 in the direction of the vector v is equal to 4/7. Now we can move on to part B of the example. So we want to find in what directions does f change most rapidly at the point 1, 1, 0, and what are the rates of change in these directions. So we're going to find when f increases most rapidly and when it decreases most rapidly. Well, we still have the same properties of the directional derivative. So the function will increase most rapidly in the direction of the gradient at 1, 1, 0, which we already found is the vector 2, -2, -1, and it will decrease most rapidly in the direction of minus the gradient, or in the opposite direction of the gradient. And that's going to equal the vector -2, 2, 1. So these are the two directions giving where our function is going to change most rapidly. And the rates of change in both of these directions are respectively just the magnitude of the gradient of f at 1, 1, 0, which will be equal to 3, and then minus the magnitude of the gradient of f at 1, 1, 0, which will be equal to minus 3. I also don't know why I have these absolute value signs. But yes, so for this example, we have just taken the idea of the directional derivative and generalized it to functions in 3 variables, and then also generalized the properties that we have for the directional derivative to find the directions in which f is going to change most rapidly. Finally, the last thing to get through for this video, it's just a real short section here at the end of section 14.5. We are going to find a nice way to write down the chain rule for paths in space. So if we let r of t, which is equal to x of ti plus y of tj plus z of tk, so we have our component functions here, and it's a smooth path in space, and w is equal to f of r of t. So the function f is going to take in points on the curve r of t and output some scalar w. So f is still going to be a scalar function evaluated along the curve c. Then the chain rule from section 14.4 tells us that the derivative of w with respect to t is equal to this long expression here that I won't say. But we can rewrite that expression as the dot product of two vectors. So in the first vector we have partial w with respect to x, partial w with respect to y, and then partial w with respect to z. And we have the dot product with dx dt, dy dt, and dz dt. But remember that dx dt, dy dt, and dz dt, this vector here, is the same as the vector corresponding to r prime. So that's the derivative of the function r, the vector valued function r. And on this side, the vector on the left-hand side of the dot product, that is going to be the gradient of f. And so ultimately we can write that the derivative of w with respect to t is equal to the gradient of f of r of t, where again r of t is the curve, dot product with r prime of t. So this is actually going to be another way to write the chain rule for paths that are described by vector valued functions r. And so I put this in a box down here. The derivative along a path is given by, and on the left hand side we have the derivative with respect to t of f of r of t is equal to the gradient of f of r of t dot product with r prime of t. So this is another way to write down the chain rule for a function in 3 variables along some path given by r. And this will be important in section 14.6. I think it's mentioned right at the beginning. So this is the end of the material for section 14.5, and hopefully you can look forward to section 14.6.